So in the last session we defined the simple extension for an element over a field. The definition of a simple extension is simple extension goes like this. If E is a extension of F and alpha belongs to E, then the simple extension for alpha over F denoted by F of alpha is the smallest field containing alpha and F. So if alpha belongs to F, then F of alpha is equal to F, because that contains both alpha and F. So our interest is when alpha is not in F but in a E. So it's going to be like this. This is E and this is F. Our alpha is somewhere here. If it's already in F, that is of no interest for us. So we are trying to find out a field that contains F and alpha. And we already have a example like E is equal to R and F is equal to Q and alpha is equal to root 2. Where here alpha, the root 2 is algebraic over Q. We are going to do some more examples. Okay, basically not on infinite field but on finite fields. So we'll start with a known finite field. Then, see, we are going to work with the algebraic elements, not with the transcendental elements. Okay. So we want to pick an element outside F. If it's already in F, that's not what we want. But outside F, at the same time it's algebraic over F. That is a kind of element we want to choose. So choose an element. Choose an element not in the base field but algebraic over the base field. Well, I'll call this as F. So we don't want to call again and again base field. This is F and this is F. When the element is algebraic, then there exists an irreducible polynomial over f of x. Okay, so construct an irreducible polynomial over f such that the element is a 0 of the polynomial. In fact, what we are going to do is, we are going to construct the polynomial first and assume that there exists an element that becomes a 0 of the polynomial. Okay, let's start like this. Start with a known finite field. What are the known finite fields? We have some known finite fields. Any field of this form, Zp, this is actually where P is a prime, 0, 1, 2, P minus 1, this is a finite field. So we will take the smallest one. Our F is going to be Z2, and that contains just 2 elements. And we are going to construct a irreducible polynomial over C2 of x. Okay, so construct an irreducible polynomial over Z2 of x. The polynomial which we are going to consider is P of x equal to x square plus x plus 1. And how do you show that this is an irreducible polynomial over this finite field? If it is a reducible polynomial, then if you substitute the elements from Z2, somewhere you should get a 0. Then that is a reducible polynomial. So if you put P of 0, that is actually 1. P of 1, that's actually again 1. So those are the only values you can put in here. So none of them, the values of those 2 elements over this polynomial is not equal to 0. So this is actually a irreducible polynomial. So P of x is irreducible. Now we have a theorem. F is a field and P of x belongs to f of x. Then there exists an extension of f that contains the 0 of P of x. Right? So definitely there is an extension here. This is irreducible, so the zeros are not inside this. Zeros are outside Z2. But there is a field outside C2. There is an element outside C2 that can be a 0 of this polynomial. We don't know what that element is. So let us assume that let alpha be the 0 of x square plus x plus 1. Now we will consider Z2 of alpha, the simple extension containing Z2 and alpha. This is our Z2, just 0 and 1, and we have a polynomial here x square plus x plus 1. The 0 is not inside this, so it is outside here. So we are going to find out the elements of the field that contains both alpha and Z2. and that is what we call it as the simple extension for alpha over Q. Because P of x is algebraic, the P of x is a irreducible polynomial and alpha is a 0 of this, alpha is algebraic over Z2. That implies alpha is algebraic over Z2 of degree 2, because the degree of this polynomial is 2. Actually, in other words, irreducible polynomial of alpha over Z2 is x square plus x plus 1, and the degree of alpha Z2 is equal to 2. So what can you say about if it is algebraic over Z2, then Z2 of alpha will always be like this: A plus B alpha, A comma B belongs to Z2. It's a polynomial. This contains the polynomial in alpha of degree less than the irreducible polynomial of alpha. Exactly like what we did in the case of Q root 2 is equal to A plus root 2B or B root 2. A and B belongs to Q. But here A and B are infinite. It can be anything. It's in Q. Q is an infinite set. But in this case, A and B are from Z2. So the values of Z2 alpha is finite. So you put values A and B 0 and 1. So you get 0, 1, alpha, 1 plus alpha. When both A and B's are 0, you get zeros. Then A is equal to 1 and B is equal to 0, you get 1. A is equal to 0, B equal to 1, then you get alpha. When both of them are 1s, you get this. So, this is a field of 4 elements. What do you know about alpha? All we know about alpha is an element that is a 0 of this polynomial over f of x or over C2 of x. Just like x square plus 1 belongs to Q of x, and the root of or 0 of this polynomial are i's. It's an imaginary number. We don't know the value of that. We call it as an imaginary number. Just like that, we have an alpha here. We don't know exact value of that. All we know is this is the 0 of this polynomial. But we can find more about this. We need to know more about this element, in the sense that how do you multiply and add with elements of Z2. So we'll try to find out the multiplication and addition tables for this. See, for addition and multiplication, because it's a finite set, we can always come up with the addition and multiplication tables. Let us start first with the Z2 only. 1, 0, 1. 1, 0. So this is 0, 1, 1, 0. 1 plus 1, 0. Here it is 0, 0, 0, 1. this is our base field Z2. Now we have two more elements coming in, alpha 1 plus alpha, alpha 1 plus alpha. Then we have to fill up the whole thing. Then we know exactly how we can add and multiply alphas with other elements from Z2. Same here, how to multiply. So definitely 0 is an additive identity. So this is going to be alpha 1 plus alpha, and this is going to be alpha 1 plus alpha. Alpha plus 1, 1 plus alpha. Alpha 1 plus alpha, this is also 1 plus alpha. 1 plus 1 plus alpha, actually 2 plus alpha, but 2 is 0. Then here it is alpha plus alpha, 2 alpha, 0. Alpha plus 1 plus alpha, alpha plus alpha, 0, 1. This will be 1 plus 1 plus alpha, 2 plus alpha, that is 0 plus alpha, that is alpha. This will be 1 and this will be 0. So here we are going to do what we are going to see. This is 0 and this is also 0, this is 0 and this is also 0. And if you multiply by 1, it is going to be 1 plus alpha, multiplied by 1, alpha 1 plus alpha. The only problem is this square. Alpha times alpha, actually it's alpha square. What do you know about alpha? Alpha is a 0 of P of x. So P of alpha is equal to alpha square alpha plus 1, and that is equal to 0. That implies alpha square equal to minus alpha minus 1. And that implies 1 plus alpha or alpha plus 1. Why? Because the additive inverse of alpha is alpha, additive inverse of 1 is 1 in Z2. So here alpha square is 1 plus alpha. Alpha square is 1 plus alpha. This will be alpha plus alpha square. Alpha plus alpha square is equal to minus 1. And that is actually equal to 1. Because additive inverse of 1 is 1. So this will become 1. And here this will be same 1. And here it will be 1 plus alpha times 1 plus alpha. 1 plus 2 alpha plus alpha square. 2 alpha is gone because that is 0 in Z2. Alpha square plus 1 is alpha. Alpha square plus 1 is minus alpha, which is alpha. So this is alpha. So we know everything about this field. This has got 4 elements, and we know how to multiply and add these elements with the other elements of the base field. One thing we need to do is, when you are filling up the tables, all these fields are that they should come from these 4 elements. We cannot go beyond that. If it's alpha square, then we have to reduce it to some elements from here, and that's what we did. We need to do one more. We need to do one more thing before we finish this example. That is, see, alpha is a 0 of this polynomial. So alpha is a 0 of x square plus x plus 1. This is a polynomial of degree 2. So if you are factorizing this, see, when you take q and root 2 and x square minus 2, root 2 is a 0 of this, then x minus root 2, x plus root 2, they are two factors of this, and this belongs to q root 2 of x, does not belong to q of x, but still you can factorize it in the simple extension field. So we probably may not be able to factorize within z2 of x, not probably, we cannot factorize within z2 of x, but we can definitely factorize this over z2 of alpha of, we can factorize z2 alpha of x. This means that polynomial over x with coefficients from z2 of x, not just z2 of alpha. Because root 2 is a 0 of x square minus 2, definitely we know that x minus root 2 is a factor of this. And what we did is, we can do a division. So our objective is to factorize this using alpha. So since alpha is a 0 of x square plus x plus 1, x minus alpha is a factor of x square plus x plus 1. And we are going to find out the other factor because this is a quadratic polynomial or polynomial of degree 2. So what we do is we do a long division. X square plus x plus 1, x minus alpha, x minus alpha. So this is x square minus x alpha. So when you subtract, it will be 1 plus alpha times x plus 1. So here it will be 1 plus alpha. So multiply 1 plus x alpha times x minus alpha square. And when you subtract, it will be 1 plus alpha square. And this is actually equal to 0 because p of alpha is 0. So the factors of this are x square plus x plus 1 equal to x minus alpha times x plus 1 plus alpha. So this is going to be the picture is going to be like this. Here it is z2, this is c2 of alpha. Alpha is somewhere here. Okay, so this is the smallest field containing z2 and alpha. Just like q root 2 and q and root 2 c. We will do a problem, and before we get into the problem, I want to see how we can express differently the simple extensions when it is transcendental and algebraic. Let us assume that we have an extension here. E is an extension of f, and alpha is, or alpha belongs to E. So there are two cases here. One is alpha is transcendental. Second one is alpha is algebraic. When alpha is transcendental, f alpha is the quotient of polynomials in alpha, like p of alpha by, or let us say r of alpha by s of alpha, where r of x comma s of x belongs to f of x. This is the definition of the simple extension of alpha when it is transcendental. This is actually the field of quotients. But when alpha is algebraic, this means that there exists an irreducible polynomial in f of x. Let us say irreducible polynomial p of x, or let us say r of x in f of x, such that r of alpha is equal to 0. Then let us assume that, degree of alpha over f is equal to n. Then f of alpha is some polynomials in alpha where the degree of, where the polynomial is in f of x and the degree of p of x is less than n, strictly less than n. This we can write it as by 1. And 1 is also a polynomial in f of x. So to make something very similar to this, we can say that this is actually q of alpha, where q of alpha is always 1. So if you don't know whether transcendental or algebraic, we can write the simple extension of alpha as r of alpha by s of alpha r of x comma s of x belongs to f of x. Where when it is algebraic, this is always 1. And this is actually, there is a restriction when alpha is algebraic. This polynomial will be less than, the degree of this polynomial will be less than the degree of the irreducible polynomial of alpha over f. And s of x is always 1 when it is transcendental. But when it is algebraic. When it is transcendental, then there is no restrictions on this. But still we can write it like this. Now we'll define the problem. Just want to make sure that you understand how to express the simple extensions as a quotient of polynomials in alpha. Now the problem is, let E be the extension of f. Then I'm going to take two elements, alpha and beta, in E. all we know is alpha is transcendental. Over F. That means that alpha does not belong to F. It's outside F. And this is transcendental over F, but is algebraic over F of beta. Then what can you say about alpha n? So what is the relation? What is the relation between alpha and beta? We don't know anything about beta. It could be a transcendental element, or it could be an algebraic element. But all we know is alpha is algebraic over f of beta. So f of beta, we know that f of beta can be written like this: r of beta by s of beta, where r of x comma s of x belongs to f. We just now saw that either it is transcendental or algebraic. So any element from here can be written like this. We know that alpha is algebraic over f of beta. So alpha is algebraic over f of beta means, what does that mean? There exists a polynomial. There exists a polynomial. Let's say p of x in f of x. No, in see, alpha is algebraic over f of beta, not f. Okay, so there exists a polynomial in p of x in f of beta of x. This means that the collection of polynomials with coefficients from f of beta. Of degree n for some m. For some n. So let p of x equal to a0 plus a1x plus dash dash an x to the power of n, where a belongs to f of beta, not f of beta. This is a polynomial of over f of beta. And we know that p of alpha is equal to 0 because it is algebraic. And this is a reducible polynomial. Now, let us substitute a0s with some elements like this. So this will be r0 of beta by s0 of beta plus r0 or r1 of beta by s1 of beta of x plus dash 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 plus rn of beta by sn of beta xn. These are all some kind of polynomial in beta, because any element from f of simple extension of beta over f can be written like this. So these elements are all from f of beta, so we can write it like this. For some Ri of x Si of x in f of x. We know that P alpha is equal to 0. So we can substitute x with alpha and get the whole value as 0. P of alpha is equal to 0 implies R0 of beta by S0 of beta plus R1 of beta by S1 of beta alpha plus dash 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 plus Rn of beta by Sn of beta alpha to the power of n equal to 0. This is a finite sum of quotients in polynomials in beta and alpha. So what we are going to do is, we are going to multiply the product of this from left hand side and right hand side. I am not going to write the whole thing, but I am going to write it like this. This implies R0 bar of beta. This R0 bar beta means this multiplied by the product of this. So it will be S0 will be cancelled out. So this will be R0 times S1 beta times S2 beta dash 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 Sn beta plus R1 of beta alpha plus dash 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 plus Rn beta of alpha n is equal to 0. This is a polynomial in alpha, but the coefficients are also polynomial but in beta. So when you expand this and regroup alphas together and make it as a polynomial in beta, we can write it like this: R dash 0 of alpha plus R dash 1 alpha beta plus dash 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 plus R n dash alpha beta n is equal to 0. Because these are all finite elements, this will be P elements, this will be Q elements, something like that. So you expand it and regroup alphas together and make it a polynomial beta. This implies beta is algebraic over f of alpha. Because if you take the polynomial as R0 alpha plus R1 dash alpha times x plus dash 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 Rn prime alpha of x to the power of n. If you take that polynomial, beta will be a 0 of that polynomial. So beta is algebraic over f. So that is the relationship. If alpha and beta belongs to E and alpha is algebraic over f of beta, then beta is algebraic over f of alpha. If you write a picture like this, if you draw a picture like this, E, this is f, there is an f, alpha here, so beta here. We know that alpha is algebraic over f of beta. This is f of beta, containing beta and f. If beta is algebraic, if alpha is algebraic over beta, then beta is algebraic over f of alpha. That is the relation between alpha and